Pluto, the astounding peewee planet. Living at the outer extents of our planetary gathering, Pluto is stirring up intensity within the cosmic neighborhood. Reports indicate a possible encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of this celestial struggle. But how did Pluto end up on a collision course with its distant neighbor? Furthermore, what could this inescapable impact mean for us here on Earth? We should examine this unfolding event. Once considered an evident planet, Pluto was later reclassified as a dwarf planet due to its unusual orbit. Despite this change, it continues to fascinate and engage space specialists. Recent predictions from observational scientists highlight a concerning proximity between Pluto's orbit and that of Neptune. These experts warn of a possible collision between the two planets, which could pose a significant risk to Earth. Pluto's journey around the Sun is marked by its unique characteristics within our solar system. Its orbit takes an astonishing 248 years to complete, and since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun. Adding to its intrigue is the highly elliptical shape of its orbit, a departure from the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its path more extreme compared to other planets. One extraordinary aspect of Pluto's orbit is its intersection with Neptune's path. For approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational influences exerted by other planets. The peculiar nature of Pluto's orbit was recognized shortly after its discovery, presenting a fascinating puzzle for astronomers. Unlike most planets, whose orbits remain relatively close to the ecliptic plane, Pluto's unusual features include a steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit, despite these complexities, serves as evidence of the intricate mechanics governing celestial bodies. The three-body problem in space involves understanding the motion and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This concept explains the unpredictable interplay of their orbits and gravitational forces. Terms like apsidal precession, libration, and the Kozai mechanism contribute to unraveling this cosmic mystery. Astrophysicists confirm that the libration effect, which helps maintain planetary stability, plays a crucial role in the relationship between Pluto and Neptune. This phenomenon ensures that when Pluto crosses Neptune's orbit, it remains at least 90 degrees away from Neptune, effectively preventing potential collisions. Libration also guarantees that when Pluto approaches Neptune or other giant planets, it remains positioned well above their orbital plane, providing an additional safeguard against impacts. The Kozai mechanism explains why Pluto's orbit appears chaotic yet remains stable over long periods. Despite apparent irregularities, numerical simulations conducted in the late 1980s revealed that Pluto's orbit, while seemingly unpredictable, is actually stable over incredibly long timescales. Small initial deviations can lead to significant differences over millions of years, yet Pluto's unique orbit maintains its stability through the interplay of gravitational forces. Recent computer simulations have enhanced our understanding of how massive planets like Neptune, Jupiter, and Saturn influence Pluto's trajectory around the Sun. Neptune's special relationship with Pluto, completing 3 orbits for every 2 of Pluto's, significantly contributes to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity plays a crucial role, while Saturn's influence, though smaller, also contributes to Pluto's long-term stability. Through extensive simulations, researchers have demonstrated that the combined gravitational effects of Neptune, Jupiter, and Saturn ensure Pluto's secured and stable evolution in space over billions of years. These gravitational interactions are essential for maintaining order in the solar system. Without them, the solar system would be prone to greater chaos, unexpected behaviors, and potentially catastrophic collisions. Understanding Pluto's orbit is particularly crucial in discussions about a possible future collision with Neptune. This knowledge provides a clearer picture of the dynamic nature of our planetary system. Pluto's case illustrates how seemingly unstable orbits can achieve equilibrium through the complex interplay of gravitational forces and orbital mechanics. Continuous observation and analysis of these phenomena are essential for gaining a better understanding of our place in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime example of this uncertainty. The concept of orbital chaos highlights the delicate dependence of a celestial body's path on its initial conditions. In Pluto's case, even slight variations in its position or velocity can significantly alter its long-term orbit. Automated simulations have been instrumental in helping researchers understand how Pluto moves through space. By making small adjustments in these simulations, space experts can observe how minor changes can have a major impact on Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's orbit. Despite factors like apsidal motion and libration contributing to its stability, Pluto's orbit can still exhibit unexpected irregularities. Even the slightest changes can have profound effects on its long-term path. Beginning contrast in Pluto's situation. Or then again, speed can prompt significant changes in its direction over numerous years. In spite of this inborn tumult, Pluto's circle stays stable for an apparently forever spanning billions of years. This proposes that, underneath its obviously capricious appearance, Pluto's excursion around the Sun follows a coordinated order, assuming tremendous occasions. Foreseeing the future paths of divine bodies, particularly those like Pluto that have uncommon orbits, is very challenging. The inborn eccentricism of these frameworks makes long-term projections questionable. Numerical recreations help us comprehend and anticipate future movements of celestial bodies, yet they likewise reveal the constraints of our predictive abilities. These models heavily depend on precise initial conditions and simulate complex interactions. Even a small error can prompt vastly different outcomes, making exact predictions difficult. The chaotic nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our still limited knowledge. The gravitational effects of massive planets on Pluto's orbit provide critical insights into the broader dynamics of the planetary system. It demonstrates how every planet's presence and position can influence the stability and direction of other bodies in the system. Regardless of these complex forces, notable astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such a crash, seemingly unlikely given these intricate dynamics, is now a topic of concern. Neil deGrasse Tyson, a well-known astrophysicist, offers an interesting perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet rather than a full-fledged planet, shares insightful thoughts on how our understanding of celestial mechanics is constantly evolving. Tyson views Pluto's reclassification not as a downgrade, but rather as a necessary adjustment to our growing knowledge of the diverse objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much more there is to discover in space. Tyson believes that the allure of these questions makes astronomy so captivating. He also understands how space-related events and discoveries shape public interest in astronomy. Events like Pluto's reclassification and its unusual orbit are great opportunities to capture the public's imagination and curiosity about the universe. By examining the dynamic and, at times, counterintuitive aspects of celestial mechanics, Tyson aims to foster a deeper understanding and appreciation of the universe. He actively works alongside other scientists to inform the public about potential risks posed by Pluto's unpredictable orbit. After extensive research on Pluto, Tyson has raised concerns that the three-body problem could pose a serious danger, suggesting that a collision with Neptune is long overdue. Furthermore, Tyson emphasizes how such an impact could disrupt the balance of the solar system and lead to catastrophic consequences, potentially even affecting Earth. A collision between Pluto and Neptune would be an extraordinary and devastating event in our solar system. Such an impact would release an immense amount of energy, possibly destroying Pluto due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, posing potential risks to other planets and their moons. For Neptune, such a crash could alter its atmosphere and orbit, depending on the specifics of the impact. Michio Kaku, a renowned theoretical physicist known for his work in string theory and science communication, offers a unique perspective on this situation. His views on the future of space exploration and the relationship between celestial mechanics and theoretical physics provide deep insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer crucial insights for future space missions. This knowledge can aid in navigating the solar system more efficiently, anticipating potential threats, and planning missions to the outer regions of our planetary system and beyond. Kaku stresses that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for approaching and understanding distant worlds. In discussing planetary physics, Kaku often highlights the deep connection between celestial mechanics and theoretical physics. He believes that planetary movements and interactions, such as the gravitational relationship between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, seeks to unravel these principles at the most fundamental level. He suggests that studying the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also addressed the potential collision, relating it to his theories about the universe. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. An impact of such magnitude in our solar system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extraordinary circumstances, an essential focus in string theory. Additionally, the gravitational waves produced by such a collision could provide valuable data for testing predictions of string theory related to gravity and spacetime. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be enormous, potentially contributing to our understanding of the fundamental nature of the universe as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a remarkable example of celestial mechanics, demonstrating both stability and chaos within our solar system. The unique characteristics of its orbit, shaped by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. The universe holds countless mysteries, and the three-body problem is just one of them. There are other potential cosmic catastrophes that researchers anticipate. While the chances of planetary collisions in space are extremely low, they are not entirely impossible. The way planetary orbits are influenced by various factors, including gravitational interactions, is explained by the three-body problem. In some star systems like TRAPPIST-1, which contains 7 Earth-sized planets, gravitational forces create a rhythmic pattern called orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the tightly packed nature of systems like TRAPPIST-1, collisions are not currently occurring. Researchers closely monitor these systems to understand how planets influence each other's orbits, particularly when they are in close proximity. This knowledge helps us grasp planetary evolution in space. Rogue planets, drifting through space without orbiting a star, introduce another unpredictable factor. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events, such as the passage of a nearby star or dynamic instability in their home systems. Over time, These wandering planets can travel vast distances, possibly reaching areas far from their origin. During their solitary journey, there is a chance they could encounter another star system. If a rogue planet were to enter a nearby planetary system, there is a slight possibility of a collision with a planet in that system. However, given the vast and overwhelmingly empty nature of space, the probability of a rogue planet directly impacting another planet is extremely low. The vastness of interstellar distances and the relative rarity of rogue planets compared to the number of stars and planets in stable orbits serve as barriers against frequent collisions. Furthermore, rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such encounters even more unlikely.